Hello students, welcome to aimsindia online classes. This is a chemist session. Here we are discussing about chemical bonding chapter. Okay, in this session especially we are going to say about bond parameters. Okay, parameters. What is meant by bond parameters? What are those? We are going to see in this session. Covalent bonds can be characterized on the basis of several bond parameters such as bond length, bond angle, bond order, and bond energy, which is also known as bond enthalpy. So these we can say as bond parameters. These bond parameters offer insight into the stability of a chemical compound and the strength of the chemical bonds holding its atoms together. Okay, these bond parameters give information about or insight into the stability of these chemical compounds, and even the bond strength also can be expected based upon these bond parameters, which is, now let us say about bond length. The equilibrium distance between the nuclei of two covalently bonded atoms is defined as bond length or bond distance. Say for example, these two are the atoms which are participating in the covalent bond formation. Now, this is the distance between the two nuclei of these atoms. So if you are able to calculate this distance, this is called bond length. The distance between the nuclei of two covalently bonded atoms is defined as the bond distance. Okay, the bond length is usually expressed in angstrom units because, as we are dealing, this is the distance between the nuclei of two bonded atoms. As it is distance, it is measured in terms of centimeters, millimeters, and even as it is micro quantity, generally used units are angstroms or picometers. Okay, we know 1 angstrom is equal to 10 to the power of minus 10 meters, and 1 picometer is equal to 10 to the power of minus 12 meters. So they are generally used units for measuring bond length. Okay, did you get it? What is meant by bond length? The distance between the two nuclei of two covalently bonded atoms in a molecule is generally defined as bond length. In ionic compounds, the bond length is the sum of the ionic radii of positive and negative ions in a crystal. However, in a covalent compound, the bond length is equal to the sum of the covalent radii of the atoms constituting the bond. See here, generally in ionic compounds, it is defined or it can be considered the bond length as the sum of the ionic radii of positive and negative ions. Whereas if you see in covalent compounds, the bond length is equal to the sum of the covalent radii of the atoms constituting the bond. Suppose this is a covalent compound and here the covalent bond is formed between these two atoms. And now the bond length can be expressed as the sum of the covalent radii of these two atoms. The sum of these two covalent radii is considered as the bond length in that molecule. The bond length depends upon the size of the atoms and the nature of the bond also. If the atom's size is bigger, then the distance between the two nuclei will be greater and hence the bond length will be greater. Isn't it? If the size of the atoms is less, what happens? The distance between the bonded atoms will be less and hence we can say bond length is less. In the same way, the nature of the atoms participating in the bond formation or the nature of the bond also will affect the bond length. Because in certain bonds, the extent of approaching each other will be greater and hence the bond length decreases. If the bond is stronger, the atoms will be held closely together and hence we can say bond length less in that case. If the bond stronger bond, if it is weaker bond, then the atoms will be held loosely and they'll be a little apart from each other when compared, and hence bond length will be greater in that case. Okay, in that way bond length depends upon the size of the atoms participating in the bond formation. At the same time, the nature of the bond also will affect it. Okay. Bond length increases with the increase in the size of the atoms. Yes, for example, bond length of Hx are in the order. Hi is greater than Hbr, which is greater than HCl, and it is greater than Hf. If you observe here, in all the molecules, one atom is being common, hydrogen. Whereas if you see the other atom is being halogen, in the place of X it is considered here halogen. These all are belong to same group, halogen group, that is 7th A group. Out of these atoms, the size increases from fluorine to iodine because they all belong to same group. From top to bottom, that is from fluorine to iodine, size of the atoms increases in the group. This is due to increase in number of shells from element to element, isn't it? Now, among these all, iodine is having greater size. So as size increases, the distance between the nuclei of hydrogen and iodine increases, and hence we say bond length is greater in this case. Whereas if you see, fluorine is having the smallest size among these all. Now, the distance between the nuclei of hydrogen and fluorine will be less when compared to this. And thus we can say bond length in case of hydrogen fluoride is smallest, and it is highest in case of hydrogen iodide. So in this way you can say bond length increases with the increase in the size of the atoms participating in the bond formation. Okay, next point. Bond length decreases with the multiplicity of bonds. Multiplicity of bonds means multiple bond formation. If there is only one covalent bond between the atoms, then bond length will be greater. If the same atoms, if they form more than one covalent bond, by the form of sharing of more than one pair of electrons between them, that is called multiple bond. As the multiplicity of bond increases, bond length decreases. For example, if you say bond length of carbon-carbon bond, that is single bond between two carbon atoms, is 154 picometers, whereas carbon-carbon double bond length is 134 picometers. Okay, as number of bonds between the atoms increases, bond length decreases. So as number of bonds increasing, the attraction between the atoms increases, and hence they come a little closer. As they come close, bond length decreases. See here, the bond length of carbon-carbon bonds are in this order. If we say both the carbon atoms are connected with a single bond, then the bond length is 1.54 angstroms. If both the carbon atoms are connected with a double bond, then the bond length is 1.34 angstroms. If both the carbon atoms are connected with the triple bond, means three pairs of electrons are shared, then these two carbon atoms comes a little more closer. Hence the bond length decreases to 1.2 angstroms. Observe here, as the number of bonds increasing, bond length decreased. Okay, that is said here, as the bond length decreases with the multiplicity of bonds. Got it? So as the number of bonds between the two atoms increases, both the atoms will be held more together and they come a little closer, and hence bond length decreases. Next parameter, that is bond angle. The angle that is formed between the adjacent atoms bonded to the central atom in a molecule is called bond angle. Say suppose here the water molecule. In the water molecule, two hydrogen atoms are connected to central atom oxygen. Now the angle that is formed between the adjacent hydrogen atoms in this molecule with the central atom is called bond angle. So here the angle created between the two hydrogen atoms with respect of hydrogen oxygen atom central atom is called bond angle. The angle that is formed between the two adjacent atoms bonded to the central atom in a molecule is called bond angle. Covalent bonds are formed by overlapping of atomic orbitals. We know this, isn't it? Due to the directional character of atomic orbitals, the covalent bonds in a molecule are oriented in specific direction. That's why we say covalent bonds are directional. The bond angle is defined as the average angle between the lines representing the orbitals containing bonding electrons. Okay, it can be simply defined in case of covalent bonds as the bond angle is defined as the average angle between the lines. See here the lines representing the orbital containing bonded electrons. Okay, that represents bond angle. Generally, bond angle is expressed in degrees, minutes, and seconds. For example, HCH bond angle in methane molecule is 109 degrees 28 minutes. Suppose if you have considered this molecule, it is called methane molecule CH4. In this, for the central atom carbon, 4 hydrogen atoms are connected with covalent bond formation. Now, we defined bond angle as the angle formed between two adjacent atoms which are connected to the central atom is called bond angle. Now if you observe the distance or the angle created between these two hydrogen atoms is 109 degrees 28 minutes in this molecule. Okay, this is pronounced as 109 degrees 28 minutes. For each degree 60 minutes exists. Okay, each 60 minutes together consider as 1 degree. So it is considered now as bond angle in methane molecule as 109 degrees 28 minutes. Here also you can say the same. Between these two hydrogen atoms also the bond angle is said to be 109 degrees 28 minutes. Here also the same. And here too. Between any two atoms in this molecule, the bond angle will be 109 degrees 28 minutes. Similarly, FBF bond angle means the bond angle in boron trifluoride molecule is 120 degrees. Means between two fluorine atoms, between the bonds of two fluorine atoms which are connected to central atom boron, the bond angle will be 120 degrees. Here also the bond angle will be 120. Here also the same. Okay. In the same way, HNH bond angle in ammonia molecule is considered as 107 degrees. Okay. In this way, the bond angle is defined as the angle between the two bonded atoms to the central atom is called as bond angle. Next parameter is bond order. The bond order of covalent bond is the total number of covalently bonded electron pairs between two atoms in a molecule. It can be found by the drawing the Lewis dot structures of the molecules and counting the total number of electron pairs between the atoms in that given molecule. Okay, bond order can be defined as the total number of covalently bonded electron pairs, or simply to say the total number of bonds between two atoms represents the bond order. It can be the bond order can be found easily by drawing the Lewis dot structures for that molecule and by counting the total number of electron pairs which are shared between the two atoms gives its bond order. Single bonds have a bond order of 1. If we say in the hydrogen molecule there exists a single bond. So a single bond represents bond order 1. If it is double bond, then the bond order is said to be 2 because in the double bond formation, two pairs of electrons are shared. So we can say the bond order in the molecules where the double bond is formed is said to be 2. In the same way, triple bonds have a bond order of 3. Say in this molecule, nitrogen, there is a triple bond. Now in this molecule, the bond order is said to be 3 because 3 pairs of electrons are shared between these two atoms. Okay, the number of pairs of electrons shared between two atoms gives its bond order. Okay, for example, if we say the bond order of the carbon hydrogen bond in acetylene molecule, C2H2 is called acetylene or ethine. commonly. Okay. In this molecule, if you see, the connection between the atoms is like this. The covalent bond formation is like this. Between the carbon-carbon, there exist three pairs of electron sharing. Whereas in between the carbon and hydrogen, there is a pair sharing of a single pair of electrons. Now, the bond order between carbon and hydrogen is 1 because they're existing a single covalent bond, or they're existing sharing of a single pair of electrons. Hence, the bond order here it is 1. Whereas the bond order between the carbon and carbon bond order is 3 because between the two carbon atoms here we can say sharing of 3 pairs of electrons, and hence the bond order is here 3. Again here between the carbon and hydrogen bond order is said to be 1 because there existing sharing of only one pair of electrons. Okay, based upon the number of pairs of electrons shared between two atoms, bond order can be decided. In the same way, if you see one more example, the bond order of the oxygen-oxygen bond in oxygen molecule is 2 because between two oxygen atoms there is existence of two pairs of electrons sharing. Both the atoms contribute 2 electrons for sharing, and hence both the oxygen atoms they share two pairs of electrons between them in the formation of oxygen molecule. Hence bond order is said to be 2 here. In the similar way, if you see another molecule, in a carbon monoxide molecule, the carbon oxygen bond has a bond order 3. How it is? First, these two atoms when they approach each other, oxygen and carbon they form a double bond by sharing two pairs of electrons. But still, carbon will be having vacancy for two more electrons where oxygen got octet configuration. Then oxygen shares a pair of electrons for the formation of dative bond with the carbon, and thus a coordinate covalent bond will be formed after the formation of double bond, and thus this coordinate covalent bond is no more different from covalent bond once after formation. That's why these three bonds are considered together as a triple bond. That is why the bond order in carbon monoxide molecule is 3 because there is existence of 3 pairs of electrons sharing. Of course, okay. So thus the bond order in carbon monoxide molecule is 3. Okay. Next parameter is bond energy. The amount of energy required to break 1 mole of diatomic molecules in the gaseous state into their free constituting atoms is called bond energy. Suppose here 1 mole of atoms are there with the diatomic molecules. To break these all 1 mole of molecules into independent atoms, it requires certain amount of energy. There the energy utilized for converting these 1 mole of diatomic molecules into gaseous atoms is called bond energy. So it can be defined as the amount of energy required to break 1 mole of diatomic molecules in their gaseous state into their constituent atoms is called bond energy. This bond energy is also called as bond enthalpy or bond strength. Okay, it can be defined as the amount of energy required to break 1 mole of molecules in the gaseous state into respective atoms, means to break these bonds between the atoms. Energy required is called bond energy or bond enthalpy. The unit of bond energy is kilojoules per mole because we are telling this is energy required to break the bonds per 1 mole of molecules. So it can be defined, it can be taken the units as kilojoules per mole. Okay. For example, if you see chlorine molecules, if we take 1 mole of chlorine molecules in the gaseous state, then the energy required to break these all bonds between the chlorine atoms will be 242 kilojoules per mole. This can be said as bond energy of chlorine. That means to break 1 mole of chlorine molecules in the gaseous state into respective chlorine atoms. The energy required is 242 kilojoules per mole. Okay, this is said to be the bond energy of chlorine gas. Okay, next, the factors affecting bond energy. On which factors this bond energy depends. One of them is the strength of the chemical bond is directly proportional to the amount of energy required to break it. If the bond is stronger, energy required will be greater. If bond is weaker, it can be broken by supplying less amount of energy only. Okay, the bond energy is directly related to bond strength. Therefore, bond energy is inversely proportional to the bond length. If longer the bond is, it will be weaker, and hence bond energy will be less. So we can say it is bond energy is inversely proportional to bond length. That is, longer bonds have lower bond energies, shorter bonds have greater bond energies. If the bond is shorter, what happens? Atoms will be held tightly together. So to break that bond, it requires a larger amount of energy. If the bond length is longer, then what happens? Atoms will be a little far away from each other. Their breakage of that bond requires less amount of energy only. Thus we can say bond energy is inversely proportional to bond length. Next, it is directly proportional to bond order. Bond order means what we said, it depends upon the number of bond pairs between the two atoms, or the number of pairs of electrons shared between the two atoms. So if the multiple bonds have, if two atoms have multiple bonds between them, then bond energy will be greater. If two atoms are having a single bond between them, the breakage of single bond requires less amount of energy when compared to the breakage of double bond or a triple bond. So it is directly, bond energy is directly proportional to bond order. As number of bonds increases between two atoms, bond energy also, or the energy required to break those bonds also increases. And one more point here, it is bond energy is inversely proportional to the atomic radii of the atoms participating in the bond formation. So if the atomic radii, nothing but atomic size, if it is greater, bond length will be greater, and hence the energy required to break the bond will be less. So we can say bond energy is inversely proportional to atomic radii of the atoms which are participating in the bond. Okay. This is since the atomic radius is directly proportional to bond length, isn't it? Okay, that's about bond energy. So these are said to be bond parameters. Okay, thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates on recorded videos. Please visit our website aimstoday.in for the other information regarding online classes, quizzes, live worksheets, do-it-yourself activities, English classes, even for coding classes. Please visit our website aimstoday.in. Thank you.